Okay, so next up, I'm very pleased to have Ionut from Ionut. He's a software engineer with a deep interest in security topics, and he has experience working throughout the software hardware stack. So please and be welcome.
Cool. Everyone. So I want to talk to you about DICE, DICE protection environments. We hope by the end of the presentation we'll have a better understanding of what DICE and VP are and perhaps what formal verification deliverables. So I'm Ionut. I'm a software engineer and I mostly spend my time prototyping various pieces of code to help our architects make better decisions about new features. And yeah, that's me in the Mihalcea a couple weeks ago. So just to look over the agenda, so I'll start by talking about the root of trust measurement and root of trust reporting, so RTM, RTR, what they are, what they do. Then I'm going to talk about device identifier composition engine, so DICE, and how it embodies RTM and RTR, and what benefits and challenges it has. Then we're going to talk about DICE protection environment, and how it mitigates some of the problems raised by DICE. And then I'm going to go over some of the verification topics around DICE and but first off, I just wanted to mention that obviously ARM has an interest in securing all the devices that run ARM cores, so securing everything from IoT devices all the way to server grade. And we have a vested interest in ensuring that our partners can mitigate whatever is in the threat model. And in some cases, this includes DICE. But my presentation here isn't really that's focused on any ARM-specific technology, so it's just broadly about DICE and VP. So let's dive in. But first, since we're all gathered and talking about remote attestation in general, I'd show where exactly in the RATS architecture we're going to be spending our time. And I hope everyone here is familiar with RATS, but if not, you turn out and you can go and read about the architecture. It's not just for RATS. Right, so let's dive into RT and RTR. So if you have a device that implements major root on power, first thing that will run will be a root of trust measurement. So that's the first box on the left. And then the job of this box will essentially be to start the boot process. So it will load, measure, and then starts layer 0. So that could be something like firmware. Then layer 0 does whatever it needs to do to set up the platform. Then it loads, measures, starts layer 1, which could be a bootloader, and so on and so forth until you get to layer n. And at the end of the process, you hopefully have 10 measured components, and you can prove to other people that good that is. But since you have these measurements, you want to make sure that no one can tamper with them, and no one can roll back the measurements. And also, if you want to prove to other people that you're actually running that code, you need a root of trust reporting to at least sign on it. And this is exactly the role that DPM usually plays, right? So it allows the root of trust measurement and all the other software to store measurements. And it allows you to create a code that is verifiable remotely. And the DPM usually sits as a different component, as a standalone part of the component on the PCB. And for most cases, this is okay. But sometimes it's too expensive, both in terms of the actual cost of the device, or how much space to take on the PCB, or the power, or the software stack, a bunch of other reasons. It's also perhaps susceptible to some physical attacks because it's a different component, so you can probe the communication less. And that's kind of how the riot started, because Microsoft hit this problem. So they had to propose a solution, which is robust, resilient, recoverable IoT devices, or RAD. And this is an architecture for providing foundational trust services to computing devices, for example, RTM and RTR. And under the umbrella of the Trusted Computing Group, TCG, this slowly evolved into DICE over the last 10 years or so. If we look at how dice maps onto the previous diagram, we can see that the root of transfer measurements has now been labeled dice engine, and all the components now have a secret that they can use to attest themselves. So the dice engine has access to the unique device secret, and it can then derive secret for layer 0, which can derive a secret for layer 1, and so on and so forth. And this is a very high-level overview of dice. I'm going to start with some more details. Let's look at how dice works. And let's first look at some of the core principles that serve dice. So the first one we already sort of touched upon. So this is the unique device secret, or UDS. This serves as an entropy source for all the identities of all the layers that are running the device. And this is something that's provisioned by the manufacturer of the device. And it's accessible only to the root cluster measurement. And the RNA essentially uses it to compute the secrets for subsequent layers. So these secrets, named compound device identifiers, are firstly derived from the UDS, from the measurements of these layers, from any other metadata. And they uniquely identify the components in the stack. So they serve both as an identifier, but also the CDIs encapsulate also cryptographic keys that allow the layer to prove that they are who they say they are, to sign credentials for children layers, things like that. And it also includes an X509 certificate that again was signed by the parent layer. So this combination of cryptographic keys, credentials, identifiers creates this layer that is very specific to dice, and it forms essentially the way that dice is generally viewed. And if we go on to look at what the root of trust has to do with the RTM, so on power on, it starts by measuring the layer 0 software alongside the hardware state, so what device you attach, the configuration, so for example, whether the device is in debug mode, then it takes those measurements and it uses the UDS alongside with that to compute the compound device identifier for round 0, so CDI. Once it's done using the UDS, it will log access to the UDS, and no other layers can actually perhaps exfiltrate the value, and it traces its own copy. Then it prepares the handle package for the first layer of software and hands over control. And if you zoom in on the second step, you can see that the TCB component identifier, or TCI, which is essentially the measurement that was taken in the first step, is put together with the UDS for one function, which is hash or whatever you need to derive the CDI. And this derivation process is actually what's used for very similar derivation process is used for all the cryptographic keys that are needed. This sequence of events will essentially be replicated in all the layers, just to the root of trust. The plot of this on the previous diagram for measurement, we can see that the measurement themselves go into the TCB component identifier, so TCI, and then alongside with the secret for each layer, so either the UDS or the CDI, they go for one function to generate the next CDI. So this chain of CDIs forms the identifiers, but also each CDI identifies not only the specific layer that it runs on, but also its ancestry, so all the layers that it has to be in trust, and their version numbers and everything related to that. It's important to note that the CDIs obviously contain an X509 certificate for each layer, and when one of these layers wants to test itself, it passes along those certificates for the verifier to actually check. And it's also important to note that in real-life deployments, even though I've represented here the root sequence as a linear sequence of events, usually you you'd see it more as a tree because some layers would actually spawn multiple children layers. And that would actually create some problems that I'll touch upon briefly. So since we're saying that DICE might be a replacement for DPM, let's get some of the benefits. So it just provides a more compact root of trust because you don't need to interact with the DPM anymore. It offers via that cryptographic framework that creates the CDIs and the certificates. The first of which, so the CDI for layer 0 is usually signed by the manufacturer of the device. So you have a CA that's signed and then it's verifiable. You have this strong device identity because you have clear cryptographic origin for all the layers. And also because of this this property that each layer has a certificate chain for itself, you have obviously integrated certificate chain, so you can use the existing ecosystem of public infrastructure and libraries for managing experimental certificates. The attestation is both explicit and implicit, or could be both explicit and implicit. So the certificates themselves can contain as extensions measurements of the layer that they represent, but also the certificate themselves and the public key that is embedded is a direct representation of the layer. So if you apply a patch to one of the layers, then the key is changed. So that's an implicit way to show what software is doing. And it doesn't really have a huge requirement for durable storage, secure storage, apart from the UDS, because every other secret is securely running on UDS. On the challenge side, perhaps the most important one is the fact that all the layers are in charge of handling their own secrets. So obviously, if one of the CDIs is exploited, then the attacker can then impersonate either that layer or any subsequent layer. So you have to make sure that it protects all the cryptographic keys and the certificates that comes. And this is quite a difficult task, given that it's the breadth of the layers that you need to implement this in. And the way you usually done is you'd expect each parent layer to erase their secrets before handing over control to the children layers. But given the fact that in some cases you have parents spinning off multiple children, then you need to have a trade-off between the security and the performance. Whether you erase your secrets and you rewrite anymore, you keep them potentially stolen. So this is not actually the only performance problem. There's also the problem that each parent layer then has to measure the children layer, it has to generate cryptographic keys for them, it has to sign certificates. This is a lot of overhead, especially if you have a very fine layering. So if you have a lot of layers, and it's a lot of cryptography to do, especially for small devices. You can also have problems with interoperability and consistency because the DICE spec is actually quite flexible, so it allows you to use a whole plethora of cryptographic algorithms, and different layers might implement different algorithms. So you want to make sure that you work together nicely. And sealing of cryptographic keys is actually difficult. So if you want to seal and make sure that one layer can only access the symmetric key if it is in a specific state, then this becomes very difficult because if you try to update either that layer or any layer before it, suddenly you can't conceal anymore. To have those challenges in mind, it's time to think about some solutions. And the isolation environment or DP comes in exactly so I'll mitigate some of that. So the purpose of DP is to serve as an architectural component in DICE to allow DICE layers to access that functionality via an interface to allow them to manage their own state and context via handle and to manage their children as well for this thing. And it also comes into offer protection for the secrets and to allow all these layers to perhaps support some DICE-related policies like sealing. We'll look at how this maps onto the previous diagram. It looks a bit busy, but there's actually not that much difference from the previous diagram. So the whole bottom part, which is the secret handling, so handling the CDIs, the relation of CDIs, is now taken care of by the protection values, the DP. And the layers themselves, so the stuff that's running on the actual application processor, only has to deal with the measurements. So only has to take measurements of the children layers, and then it can hand those measurements over to the protection environment. The layers themselves can access their state and derive and get attestations through a handle. So you have a handle that points to your context, and you can use that to make calls that provide, for example, an attestation of a key, or to generate a new child context. The benefits that DPU brings along. So a big part of the benefit is the fact that DICE DP implements a large chunk of the DICE specification, so the layers themselves don't have to. And this means that you can have better hygiene because you can just focus your efforts on making DP better and following better practices. It also means that you're now offloading handling of secrets and caching the secrets to DP, so you don't have to rely on your application processor dealing with that. And because of this, you also have floated all the cryptographic operations to this coprocessor or whatever is running DP. Again, using the big performance cuts. Now, formal verification, and just want to preface this with the fact that I'm not a formal verification person, but just wanted to cover what has been done already and what might be relevant. So, in the context of DICE, there's already been a formally verified implementation called DICE Star, and this implementation essentially gives you the DICE agent, so the root express measurement, and the L0 components. The verification goals for this, the implementation itself, I'll get to that in a bit, but the verification goals for implementation are to make sure that all the secrets for all the layers are confidential. That the implementation follows the DICE specification properly, so they have to model the specification, and that the implementation is memory safe. This is because it compiles down in C, and that it has side channel resistance for all the components. The implementation is done in Lodestar, which is a shallow embedding of C and F star, and it has a split model of doing a platform agnostic part and a platform specific part. So if you want to port their implementation, which I think they've run it on an STM32 microcontroller. If you want to port that to a different device, then you can just re-implement the platform specific parts. For cryptography, it relies on FSR, and they had to implement a new library for verified library for dealing with the subset of AS1 and XML. So the implementation that I was talking about for STM32, when they compile that down to C and ran it based on the performance and manufacturing compared to a handwritten version of DICE. And I think it also based some no difference in the size of the implementation here. And looking forward, DP is currently still in the process of standardization. So perhaps this is a good time to do a formal verification because you can still influence the design and not have problems with backwards compatibility. But what I've heard from people working on the standards and people who would actually be deploying this, what we need is a formally verified implementation that would not sacrifice readability and maintainability. And the question I would have is this possible with current tools frameworks? Thank you.
Any questions?
I was wondering want to get your feedback on sort of the following observation. So if you have the starting point with a DPM and you want to secure an IoT device that has maybe a microcontroller. So let's say that the IoT device has a Cortex M3, but then the DPM that you put alongside of it has maybe Cortex M4, which is kind of odd in some sense because of the upper mismatch. So people came up with this idea like, oh, well, couldn't we just make it simpler? And it started off indeed as you presented with something simpler, but then it's that simpler version misses some of the features that in the big picture you also need. So you also need ways to store keys. You need the side channel system, the implementation of some cryptographic algorithms, hardware external and so on and so on. And I'm wondering, like, I'm wondering whether I want to hear your feedback, whether the initial assessment of what was wrong with the EM was maybe incorrect that led them to develop DICE. They should have maybe fixed some other problems, or we see that different. Do you think that's effect along the run?
I mean, TPMs are not free raccoons in the trench, but they're like 100 raccoons in the trench, where you have all sorts of functionalities that are maybe better virtually we can just segregated functionalities and you can just pick and mix whatever you want. So I'm guessing the whole point for moving to DICE would be to just segregate the RTM and then you don't have to carry the burden of everything else that's in PDM. Obviously, you would still need cryptography running on the generator and using maybe all the other functionality or some of the other functionality. But perhaps it's better for device manufacturers to then decide which ones they want to just move on those.
Follow on from that because TPM has some really nice features. We use receiving attestation. They just become glorified HSN. Then the TCG comes up with DICE, which is, and it's just one purpose, missing a whole bunch of features. And now we have Mars, which apparently sits between the two. And the comments on Mars, which seems to be some of the nice features of TPM, and some of the nice features of DICE and small.
I don't think I'm actually familiar with Mars. So.
DICE with symmetric keys.
Yes. Well, 6 months ago.
So it's also DCG, right?
Yes.
I don't know.
Right, that's right. So it's a Microsoft research. What found that it is a 1989 paper from back that describes and 30 years ago Microsoft research.
On the paper.
Yes. Or historian, I don't know. But this another advantage of using the over of data is that you can reconcile with points. So when the chain fault, for example, you straight up to say zero, SC is 0. Yeah. So if you go with traditional times, whereas how's the EDB, you can just store things and ask for the achieve and synthesize, then we can actually make it linear. This is one of the disadvantages of the original design that it's
it's, like, those of usage, I've often been wondering of, like, where exactly should I use it? Because, for example, on a microcontroller, on the STM32, a newer one, I would probably just use the PSA, attestation mechanism. I might be biased, but, because it does all what I need. And then if I go somewhere else, if I go into like the laptop environment, I'm probably going to use the TPM-based mechanism. If I go to a smartphone, I probably use whatever they have there, which actually is this device. Yeah. But what are some of the use cases where you say, yeah, you really have to use sites because it like provides me these extra features? Have something in mind?
I don't know.
Guidance as well as
Yeah, no. So either complete like the core root of trust for certain grades stuff that we can use that. I don't know if it's a must.
I thought guidance was also, that's maybe just my impression. It looked very promising at the beginning, but then and lots of people participated, but then at some point people realized, oh damn it, to use it I actually have to produce silicon, and that's really expensive. And then like that was the story. Risk life wasn't, it was very promising at the beginning, but then
Sam is not here. You will see the recording.
Can I ask you just a solution of, attestation using dice and the fact that the certificate chain is somewhat still gray, right? So when producing attestation, you need to show freshness. So the final attestation will be section coming from what are the warranties in terms of sorting that from to is to synthesize a new assert on top of the existing chain on the front thing, and therefore enable TLS maybe for them using external line, or would you use a different approach? Well, I have an idea how to make this usable. That's what I'm asking. Realistic problems.
I mean, I think at the end of the day, it's similar to the problem of using application results. You don't have impressions. In this case, you have application elements, and then you can, as you can produce, like encapsulate the split the chains and non-sort just prevent something to it. As a new certificate has impressions included. I think those are the options that so it's still a problem that needs to be solved. But how we deal with when you can't have the freshness like the decision results. Big solution.
Because a big selling point of DICE is that, okay, sorry. A big selling point of DICE is that it produces an external so it's just, it can reduce code that you already have in the TLS stack and just there's a missing, just like for this fundamental.
For DP, there's also part of the interface that allows you to generate the key attestation on the fly. That also comes as a kind of must be good for maybe that's.
So we can also a lot of alias so that you search for the position when you can create another on the fly. With so and where do you start the change?
I think it's part of the main. You start as part of this.
It's like tuning for an station.
think so.
Right? You never know, so.
But I'm not saying that I thought that's not works, but that's not certain.
Yeah, I wouldn't think that, thank you.
Any comments? Second question. From my side, is ARM actually about the formal verification of the DPE, or is it just that as a user, it will benefit from the formal verification? Can you say a few words about that? So, if not, then do you have some context in case someone from LinkedIn is interested in taking this forward? So, should we contact instead the Microsoft guys who have worked with the application, or is there some contact with your surroundings that you can approach to?
Yeah, so on our side now, we don't only work on our verification. We benefit as I said at the beginning, so we're interested in having that split properly. So, and our partners are interested. We would be interested. I think we would be able to not assist in the same class, contribute to the verified model, but to be able to work like this. Make the suspicions clear.
I think that's self-knowledge and start with this required text.